Previously we did a numerical example, and we derived some numerical values. We obtained y equal to 0.9665, y hat was minus 0.1086, and then we calculated error, so it was 1.0751. Our goal is to minimize this error. So how are we going to do that? So we will be using the gradient descent concept and loss functions. So using this E, what we are going to do is we are going to define a loss function. Loss function, let's say J is equal to half E square. You can choose any other form for this loss function, but this is the simplest loss function because this 1 by 2 cancels out this value of 2 when we take the derivative of loss function J. And the next one is, after this we will be using gradient descent method. So for that, let's say we have any weights. Let's talk about the output weights. So V1 new will be equal to V1 minus eta derivative of loss function with respect to V1. Similarly, V2 new will be equal to V2 minus eta derivative of loss function with respect to V2. Okay, this is really simple. So let's find the derivative of J with respect to these weights. But before that, I want you to recall that when we were approximating y hat, we found this relationship between the weights and function of x. If you recall, this v was a vector of v1 and v2. Okay, I just want you to recall this because I will be taking derivative of j with respect to v to make things simple. If I take derivative with respect to v1, v2, that will also be simple. But the reason of choosing v for derivative is that if in case we have added another neuron here, okay, this will also go to the output, we will have v3. So we will have v3. So these derivatives will increase with the number of increased neurons. So it is much better to use the vector v for derivatives, and we will obtain our values accordingly. So let's switch to the next slide. Okay, so now our loss function is, let me rewrite it, half e square, right? So in order to take its derivative with respect to output layer's weight, which are v1, v2, let's do that step firstly. This will be half, right? Derivative of e square will be 2e, and then derivative of e, but with respect to v, right? This 2 and this 2 will cancel out. So the derivative of loss function with respect to output weights will be e times dE by dV, right? Now the question is, how do we find the value of this derivative? So we know that E is y minus y hat. So derivative of E with respect to v will be, now v is constant, right? It will be constant at all the moments or instances. So this will become 0 minus dv hat by dv. Okay, so I can write the derivative of loss function with respect to output weights like this, minus, okay, minus E times, okay. Now the question is, how do we find the derivative of estimated output function? So this is really easy. We know that y hat is equal to v1 h1 plus v2 h2, or in vector form we can write it like this. For simplicity, I will be taking derivative with respect to v1 and v2, so you can understand it much better. So this will be the y hat by d1 v1. Now this term does not have v1, so we only need derivative of this, so this will become h1, right? Similarly, dy hat with respect to dv2 will be h2. So in compact form I can write it as, let's say, dvi is equal to hi, right? It's easy, it's just simple derivatives, not too difficult. So what is the next step? Now next step becomes, we have to put this value in the gradient, in the loss function derivative, and we will obtain our output weights. So let me rewrite the derivative of loss function, which was minus e, right? Let's call it equation 1, and then we derive. So this was hi with respect to v1, this was h1, with respect to v2 this was h2, right? Now these two equations are really important because we will be using gradient descent, and for gradient descent we know that for any weights, let's say v nu is equal to v minus eta. So this is let me see, yeah, with respect to dv. So v nu becomes v minus eta. So we know this, dj by dv is equal to minus e and this function, so this will be minus e, this is multiply with respect to dv. Okay, so v nu becomes v plus eta e okay, and we know the value of this estimated functions derivative, which are h1 and h2. When we will solve a numerical example in the next slide, you will understand this much better. How do we obtain v nu? Because we know the values of v, which are v1, v2. If you recall, we assume this value as 1 minus 1, right? And after that, eta we have to tune it, so I will choose 0.1. E, we already derived this was 1.0751. now dy hat by dv1, so we can calculate it from here. So dy hat by dv1, this is actually h1. We had some value, I cannot recall it, but we derived this value. And similarly, dy hat by dv2 was h2. this was also some constant value. Okay, so we have all the values on the right hand side. We have v, we have eta, we have error, and we also have this vector, and we will simply substitute it here and we will obtain v new. I will explain this in the next slide. So now we can obtain our values of new weights connected with the output. But before that, I want you to understand one concept which I did not explain in the previous slide. If you remember, we have this v new equal to v minus eta dj by dv. But we have been using this value. If you look closely, we have vi here and we have a vector here. So I just want you to know that don't get confused in this. It is actually the same thing. V is a vector. You will see here in this example, right? So when we will be solving this right hand side, we have to match this dimension. So this will also be a vector. So this will also be, for example, we have a vector of 2 by 1. So dj by dv will also be a 2 by 1 vector. Okay. So now let's solve our example. So we know that eta is a tuning parameter for the approximation of function using neural network. So let us assume we choose eta equal to 0.1. We calculated an error which was 1.0751, right? And I checked my notes. We calculated h1 equal to 0.6225 and h2 equal to 0.7311. So now we simply have to put these values in the v new, which we already derived. So v new is equal to v minus eta dj by dv. So this is actually v minus eta minus e times dy hat by dv. So this dy hat by dv is actually a vector of h1 and h2. So this becomes v plus eta e dy hat by dv. So simply we will put the values. So v vector, which we initialize in the beginning of the numerical example, I chose these values randomly. So it was 1 minus 1 plus eta 0.1. So this is the value which we have to choose by ourselves to tune the approximation. Error was 1.0751, and then we have this vector of h1 and h2, which is 0.62. I will write it up to 3 digits, so 3 decimal places, so 0.731. okay. So after solving this, our v new will be, I will write it directly over here because I already calculated it, 1.0669 and minus 0.9214. okay, so we get this vector. So if you recall, we had a value v1 equal to 1 and v2 equal to minus 1. We can also see it here. So these values will be updated with these new values. Okay, so that is how gradient descent works. So in the first iteration, we had this v1 is equal to 1 and v2 equal to minus 1. But in the next iteration, we will have new values of v. Okay, so we will be using these values. And after that, when we perform the neural network approximation, these values will be updated again and again until we obtain this criteria where e approaches to 0. But you must understand this, that This is the gradient descent for the output layer. We are only tuning the output weights which has V1 and V2. We have to repeat this process for the input weights W's as well, and also for the hidden layer. So we will be doing that in the next video.